I think I just want to add on this slide that there is another option for treatment, and that is direct filtration. And this is for the case where you have really, really high quality water all year round. So if the water is less than 5 NTU all year round, you could eliminate the flocculation, flock filter, plate settler system and just go straight to a filter. I also highlight here, it works if the raw water turbidity is low, like less than 5 NTU, and also the dissolved organics have to be low. If the dissolved organics are high, then you need to have a clarifier built in. So I think just a couple of slides on slow sand filters. I have to talk about them a little bit because I spent so much of my life working with them. And here's an interesting insight. I spent my PhD learning about slow sand filters and how they work. And then when I realized that when Jacobo Nunez asked me, what can you do to provide safe water for villages in Honduras? I immediately knew that slow sand filters were not the right answer. And there are still plenty of people who are building slow sand filters for communities, and it ends up often being a problem. They fail in many, many cases because the water is rarely clean enough to use them. So they're the first filter that was used on a widespread basis. They got really fine sand. So the sand has a size of about 0.2 millimeters. So you can try to hold up your fingers and look at what 0.2 millimeters looks like. It's very, very tiny. They have very low flow rates. Look at these numbers, low flow rates of 0.03 to 0.12 millimeters per second. Now, how do you think about that? Like Monroe just said that's a low number, but how do you know that that's a low number? Here's how I like to think about this. Compare that with compare that with the clarifier, 1 millimeter per second. So what does it mean if the flow rate is, if the velocity is, let's say 0.1 millimeters per second? What does that mean about the area required for the filter?
Does it mean the area is much greater?
Yeah, how much greater?
10 times?
Yeah. And remember, I told you this before. If someone offers you 10 times as much money, you'll be very intrigued by that opportunity. Factor of 10 is huge. So it means that a slow sand filter is likely 10 times larger than the clarifiers for an agua clara plant. So it's like, oh, this is huge. Like these are big filters. Now, here's the biggest advantage for slow sand filters. And that is if you build slow sand filters, you get to use the word Schmutzdeck. So Schmutzdeck is a German word, and it really means like filter cake. Although Schmutz, I grew up in Pennsylvania Dutch country in Berks County, Pennsylvania. And Schmutz was used by my father, who spoke Pennsylvania Dutch, to refer to the grease that we would use to grease our farm equipment. So it's, I don't know, it's grease, it's slime, it's biological stuff. I don't know, Schmutzdeck. Anyway, it's this layer of slime that's on top of a filter. And it's where most of the particles are removed. It causes a lot of head loss. And it's what, when the pressure drop through the filter, or the water level difference between what's the water on top of the filter versus what's coming out the bottom is too great, then what you have to do is you have to drain the filter and send workers out to actually shovel off this Schmutzdeck and a little bit of sand. Here's another advantage of slow sand. They're used without coagulation or flocculation. So that means you don't need any alum, you don't need any polyaluminum chloride. They just work, except they don't always, but you have nothing that you can do to help them work. So they just do what they do. And let's look at, here's a slow sand filter built in Honduras. And that was one of the student trips to Honduras. We're looking at the edge of one of the tanks. Here's a picture of a slow sand filter. And I'm guessing that this one might be in the United Kingdom. And they're showing they're showing that workers were out on this filter and they were scraping up the piles of Schmutzdeck. And they've got several different piles there. And they also have one section here that they haven't shoveled up yet. So you can see the black slimy layer that was on top of the sand that they're removing. And when they do this, so they remove some sand, and maybe if things are going well, every 30 years, you have to, you keep all this sand and you wash it. And every 30 years, you have to replace that sand that you've been taking off with each of these cleanings and put it back on the filter. And there's someone shoveling this Schmutzdeck, maybe in Colombia. Okay, I've got a whole series of slides here on multi-stage filtration, and I thought about this today, and I thought we don't need to go over this, because basically I say that multi-stage filtration is an interesting idea, but it's a bad idea. It's an approach for adding several more unit processes upstream from the slow sand filters that remove a little bit of turbidity in each one, so that the slow sand filters can be used to treat dirtier water. These end up being very expensive plants. Remember, the slow sand filter is already slow and hence big, and the additional processes that they add are also big, and they also have maintenance issues. So we're not going to go into details on this. There's some pictures of slow sand filters that went with this. This is a multiple stage filtration plant. They've got dynamic filters and roughing filters and slow sand filters. And they've got all different kinds of ways you can configure them. And one of their big problems is they got filters that have gravel in them, and the gravel gets clogged with dirt eventually. And there is no easy way to clean a gravel filter that's full of sludge. And they've tried to invent ways that kind of work, but also kind of don't work. They're also huge. And I have claimed that I am the individual on the planet who invented roofing. I invented roofs, right? Remember this? I said agua clara water treatment plants need to have a roof over them. And I have to now acknowledge that I was not the first one that had this insight. Here is a slow sand filter or a roughing filter. Maybe it was a roughing filter. And they realized that they had trouble. They were growing algae. And so they covered it. And I'm wondering, if you look at this picture, right, the tin, what's that called? The tin roofing material can be removed, so you can get at the inside of the filter, because you still have to send workers in there sometimes. And I'm wondering if you can think about, in your design of this filter, what would be the next logical iteration to make this better? So currently, in order to get in there, you have to remove some of the roof. What would you do to make this better? You should install the roof at an elevation that you can walk under it. So now we just laughed at these guys, right? Because they forgot to raise the roof. But we can also laugh at Agua Clara, because this was the very first plant that Agua Clara built. And we also ran into the difficulty of the sun causing damage in the plant. And so there are now 4 little roofs covering little tanks in this plant. And that means that in order to get access, and in order for the operator to see what's happening in any of these tanks, they have to lift the cover off. So this is like an illustration of the roof was absolutely necessary, and a roof should go where a roof should go, which is up over your head, so that you can still see what's happening in the plant. You see how these roofs actually made it worse? Because now the operator can't see what's happening inside the plant. And one of the things that you want to do in the design of a plant is make it so that the operator can easily tell what's happening. The operator shouldn't have to work hard in order to see what's happening in the plant. Okay. We talked I mentioned this idea that if you know how fast the water is going through a slow sand filter, you can tell like how big it is going to end up being, right? Because you can use Q equals V times A. Q equals V times A. So that's a really important concept. And I want to just show you how significant that concept is. So here is an aerial view from Google Earth of 2 water treatment plants in Honduras, both providing water to the same town, one serving to one set of neighborhoods and another one to another set of neighborhoods. Both plants have the same design flow rate of 20 liters per second. And I didn't cheat here. I've used the same scale when I copied these images out of Google Earth. And you can see the water treatment plants from Google Earth, and you can see that the multi-stage filtration plant is just huge compared with the Agua Clara plant. And granted, the Agua Clara plant costs more per square meter because there's more stuff inside it. But it doesn't cost as much as all that extra concrete that goes into making a huge multi-stage filtration plant. And then the other thing that it's important to remember, you know, there's a lot of people living on this planet right now. And that means that there usually isn't a lot of extra land just waiting for you to come in and build your water treatment plant. Often there's not much land, or it's in a non-ideal location, like it's on the side of a mountain. And so getting land is a big piece. So having water treatment processes that don't take much land is a huge advantage. And please remember that the next time someone tells you that the solution to wastewater treatment is to use wetlands. There may be a few places where you can treat wastewater using wetlands, but wetlands require a huge amount of land. And it is very, very unlikely that the effluent from your city that you're trying to treat is going to conveniently lined up with a place where there's lots of wetlands ready to treat that wastewater. So just remember, land is at a premium on our planet today.